Lynx is a minimalist block diagram editor implemented as a Jupyter widget, meaning you can create and edit control systems diagrams directly in Jupyter. It'll run interactively and inline in your notebooks and integrate into Python-based controls design workflows. I built Lynx because I do a lot of control systems work in Python, and the existing ecosystem does a great job with 95% of what I need, but I felt like the missing piece was just a way to graphically construct block diagrams. As a disclaimer, this isn't a simulate clone, and it's not going to be. There are half dozen blocks, no support for nonlinearities, discrete time, or event handling. There's no simulation or code generation or anything like that. What it does is create block diagrams for linear, single-in, single-out systems. I wanted this for two reasons. One, to simplify and automate block diagram algebra in complicated, cascaded, or multi-loop control architectures. And two, to create clean, code-integrated documentation for notebooks, websites, presentations, or other deliverables. Block diagrams, I think, are the best way to communicate control system architectures, and I used to do this part manually in Keynote or PowerPoint. I'll put out another video soon showing how I use this tool in end-to-end controls design, including with autodiff for linearization, nonlinear simulation, and automatic C code generation. But for now, let me just walk through a simple example so you can see what the Python workflow looks like. I'll walk through the cruise control example from early on in Astrom and Murray's Intro to Feedback Control textbook. The linearized plant model here is just a first-order transfer function mapping from throttle to speed. So we can use a simple PI controller to track the reference speed. I'm going to start here with a couple of Python constants, but obviously you usually have a nonlinear dynamics model, linearization, decomposition, stability analysis, all of that. To create the diagram and open up the editor, we can just create a diagram object and then type lynx-edit, which will open up this interactive inline widget. So first, let's do the plant model, which I'll just implement as a transfer function. Double clicking brings up the parameter editing, and I can use anything that's in the Python environment as long as it resolves to a list or a 1D NumPy array. And you can see that the actual numerical values are rendered by default, but we can also put in custom LaTeX, and I'll show that here by putting in the actual transfer function parameters. And finally, I'm going to rename this block to something meaningful and show the label in the editor. One thing I want to point out is this little validation icon in the lower left. This will turn green when we have a valid system. Otherwise, it'll show warnings like this or errors if we do something like create an algebraic loop. I'll create the controller block in basically the same way that I did for the plant. And I'm just using placeholder parameters here, and we'll come back and edit them later. Then a sum block for the error signal. And here I can just cycle through the signs for the different quadrants by double clicking. And then I'll add inputs for the reference speed and an output for the actual speed. And finally, the feedback connection. One last thing for the diagram, I'm going to add short labels to some of the signals that we care about, and we'll use this later to extract different subsystems. So reference, error, throttle, and speed. Okay, now we're basically done with the diagram. The next thing we probably want to do is save it, and the diagram object supports full serialization to JSON, so we can just type save and it'll create a JSON file with everything that we need to get the Python object or the editor state back. To do that, we just use the load class method, which I'll get to in a second. Another thing I want to mention is static rendering. So this is especially useful for different kinds of documentation. You can create a PNG or SVG of the diagram with or without background with this render function. So if I don't give it a file name, it'll just render it inline. And here I'll create a SVG with a transparent background, slideshows or whatever. And the last thing I want to mention is the template concept. So even if you have a totally unique plant model and controller design, there's still a lot of commonality in the overall controller architecture, and it can be kind of a pain to build up the block diagram from scratch. So to make this a little easier, Lynx also has a template feature, which is basically just a pre-made JSON that you can use as a jumping off point. And the closest one to this system is the feedback with transfer function plant. And once you create this from a template, you can render it, you can open it up in the editor to change it, save it, make it your own. And there's several of these. You can check out the documentation site to see them all. And all right, so that's the basic diagram construction. Next, we want to design the PI controller, and to do that, we'll update the gains and then do some kind of analysis. And to keep things simple, I'm just going to hand tune these and look at the step responses. So first, there's basically two ways to update parameters. The first is to directly update the arrays stored in the Python object. And this is the syntax for doing that. We'll update the numerator. And we can see that the numerator went from zeros to our new gains. The second method is to update the actual Python variable we used in the diagram expression up here. So the diagram stores not only the numeric value, but also the string for the expression used to evaluate it. And then when we load from a JSON file, we can give it a different namespace and it'll try to reevaluate these expressions. And it'll fall back to the default numeric value if that's not possible. In this case, we can just give it a dict with our new gains, and it'll update the controller transfer function automatically. We see warnings here that for the plant, the variables A and B aren't found, so it falls back to the default values that we originally used. But we could also edit those if we wanted to. And you see that changes here. I'm going to use the namespace approach here, but it really just depends on your preference and the application. The direct parameter editing might be better if you have state space matrices from automated linearization or something like that. So now we get to the real interoperability between the Lynx diagram and the rest of the Python ecosystem, and especially the Python control systems library. Since we've named our signals, we can extract a subsystem between any two signals using the getTF or getSS methods to extract a transfer function or state space representation. So we could get the transfer function or state space representation from U to Y, which is just our plant model. And internally, this creates a Python control interconnect block diagram and passes off all the block diagram algebra to Python control, which I guess is why we end up with an extra state in this subsystem. But we can just use minreal to get a minimal realization and remove a factor of S. And then we're back to our original plant. So for this simple step response, the two things I'm going to look at are the closed loop responses of the control U and the output Y to the reference signal R. Then I'm going to use Python control to do the step response. And I'll just copy paste some plotting code here. So with this proportional only controller, we get a pretty sluggish response that doesn't track the reference with a DC gain of 1. And let me just copy everything to one block here for faster iteration. I'll add a little more gain and some integral action to drive the DC gain to 1. So this is a simple example, but that's Lynx in a nutshell. You can edit block diagrams directly in Jupyter and get clean renderings and easy subsystem extraction with no manual block diagram algebra. I'll add another video soon that shows the complete workflow, including linearization, conversion to discrete time, and C code generation for the final discrete time controller. If you're interested, you can install from pip. Just make sure to install lynx-nb, Lynx notebook, and not just Lynx. And you can find the source code for the project on GitHub. I'll put a link to the source code and documentation page in the video notes as well. Thanks for checking out Lynx, and I hope you find it useful for your own projects.